Hello guys, welcome back to the channel. If you haven't subscribed, please make sure you'll subscribe, and if you find this video helpful, please like and share. So today we are going to look into the current mirror. We are going to design the current mirrors in Cadence software. So in current mirrors there are two topologies. One is simple current mirror and the other one is the high swing current mirror. So this is the design specification which have been given. So now we shall start implementing a current mirror. So now the design specification which is given is ID should be 150 microamps, and the overdrive voltage which is necessary is 150 millivolts. So we don't know exactly what is the threshold voltage, because theoretically there might be some fixed value, but when we simulate there will be a slight variation depending on body bias effect and this other second order effects and all. So now we are going to extract this VTH value from simulation. So now let us start designing a current simple now in order to design a current mirror we need a NMOS. We will be going to design the first current mirror with the NMOS. So we are going to design in such a way that this NMOS should sink the current of 150 microampere, and this NMOS should also have overdrive voltage of 150 millivolts. So overdrive voltage is nothing but VGS minus VT equal to 0.15, and source is at ground, so VG equal to VT plus 0.15. As I told earlier, the VT value is obtained from the simulation. So now the very first step is we shall assume we need to design for 150 microampere. We exactly don't know for what value of width that corresponds to 150 microampere. So now initially we have to assume certain things, that is we shall start the iteration with W something like say 4 micrometer. Now we shall go into the Cadence software and start designing. So we shall start assuming the width of NMOS as 4 micrometer, and we also need to obtain the threshold voltage of this NMOS, because from in simulation threshold voltage value like varies depending on many parameters. So we shall do the DC analysis. We shall save the DC operating point, and annotate the DC operating points. From this we need to obtain the value of VTH, and we also need a region also. Go to setup, then we need to annotate the NMOS. We don't need the value of VDH, instead of we shall annotate for threshold voltage, and also we shall annotate the region of operation. Once annotated, the value will start appearing here. So we got to know the threshold voltage is 459 millivolts, or I can say almost 460 millivolts or 0.46 volts. So we shall substitute here threshold voltage. We got as 0.46 plus 0.15. So when we evaluate this 0.146 and 0.15, we end up getting the value of 0.61. Now we shall fix the gate voltage which is given to 0.61 volts. So I have already fixed that value 0.61 volts. Now shall save it and run it. Okay, so for width of 4 micrometer and overdrive voltage of 150 volts, we are getting the current as 43.6 microamperes, but we need to design for the current of 150 microamperes. So how shall we go there? We know that drain current equation is in saturation mu C ox W by L V O V whole square. So if we are maintaining the overdrive voltage mu and C ox and all constant, ID is proportional to W, I can say. So I can write as ID1 divided by W1 equal to ID2 divided by W2. So we almost got 43.6 microampere for the width of 4 micro. So in order to get 150 microampere, what is exactly the width is? So W2 would be almost, if we calculate W2, it would be around 13.8 micrometer. Now we shall substitute this W2 value there and shall see like are we achieving that 150 microampere which we have designed for. So width we are giving as 13.8 micrometer. I shall check and save it and run. So we can see ID we are getting almost 156 microampere, almost near to what we are designed for. So in order to make it still closer, we shall try to reduce this width. As we reduce the width, since current is proportional to the width, as we reduce width, we can see a reduction in the current also. So we can see it started slightly reducing. So I'll still reduce further. Let me make it as 13.2 micrometer. Check and save it and run. Yeah, it's almost near. Yeah, 150 microamperes. So now we are able to we obtain the gate voltage as 610 millivolts, and we found that width of NMOS necessary is theoretically it is 13.8, but practically it is 13.2 micrometer. This is for NMOS. So now we shall construct a simple current mirror. So now we shall we know that width of NMOS we obtained is 13.2 micrometer. We shall change width of NMOS as 13.2 micrometer, and the current should be 150 microampere, the current source. So now this NMOS is capable of sinking 150 microamperes, and this terminal ensures this is always in saturation. See, we can see this is 150 microampere. Okay, now we shall implement a current mirror, simple current mirror. So simple current mirror, there is a current source which is of value 150 microamps, and there is an NMOS. So this NMOS drain and gate are shorted to ensure this is always in saturation, and there is another NMOS which mirrors the current. So we know the width, what we are seeing here, that is this NMOS is 13.2 micrometer, and overdrive voltage we are keeping as 150 millivolts. So in order to keep overdrive voltage 150 millivolts, we need VG of almost 610 millivolts or 0.61 volts, and W2, in order to mirror the same current, we are going to keep as 13 micrometer. And also the overdrive voltage, since both the gate voltage are shorted, this and this voltage, gate voltage are shorted, so overdrive voltage obviously be 150 millivolts. And this operation region, so the operation region of this NMOS should be region 2, that is nothing but the saturation. Same for this, applicable for this NMOS also. So in order to be this MOSFET to be in saturation, we have to give a DC voltage that is greater than at least a overdrive voltage. So we shall give this voltage as 0.9 volts. So now we shall implement the same in the Cadence tool. So the width of this should be 13.2 micrometer, and the width of this also should be 13.2 micrometer in order to mirror the same 150 microamps of current. And the source voltage should be, VDD, it is almost 1.8 volts, and the source voltage here should be 900 millivolts or 0.9 volts to ensure this NMOS M2 is always in saturation. Now this current source should current of 150 microampere. Now we shall simulate. So we can see this is able to sync a current of 159 microampere. What we were expecting was for 150 microampere. So now we can make it approx to 150 microampere by reducing a width. So we can make it as 13 microampere instead of 13.2, and we shall apply and we shall check it. So we can see current is getting reduced. So I'll reduce further, I'll make it as 12.6. So we can see current we got almost 151, we can say approx to 150. So we can keep the width as same, since 150 and 158 is doesn't make that much difference. So we will make it the width as it was in the original, that is 13.2, and we got a current of 150 microampere. So 159 microampere. So now we are able to design current mirror of 150 microampere. Now in order to increase the current mirroring, it is not necessary that it is capable of mirroring only the actual current. It is capable of scaling the current mirror, that is original current mirror. So now if we want to design it for 1.5 milliamps, so 1.5 I is proportional to So if we call this as I2, this as Iref, I2 equal to Iref times of W2 divided by W1. So Iref is 150 microamps, and width of if we want to design it for 1.5 mirror for a current of 1.5 milliamps, so we know width as 13.2 micro, so and width 1 and W2, so we have to find here 13.2 divided by microamps. I can say width of this is almost 10 times of W1. Width of second NMOS is almost 10 times of W1. So either we can change the width, or we can go to a multiplier and make it as 10. Check and save and run. So we can see the current is 1.6, or you can say almost 1.5 microampere, so which we are intending for. Now once this is done, now we shall obtain what is that minimum voltage necessary, across this in order to keep this in saturation, so that it will mirror the current exactly. So we had kept as initially as 0.9 volts. Now practically we shall see what is that minimum voltage, VDS min, or you can say this as headroom voltage. So in order to do that, we have to do the DC analysis. We have to sweep the current versus voltage in the x-axis. We are sweeping from 0 to 1.8 volts, and we need to plot the current. Now we shall plot the same and find out what is the headroom voltage from the graph. Let us change back that this as 150. Let me make my multiplier as 1, so that it will be sourcing 150 microampere. Yeah, now we got VDS on the x-axis and the drain current on the y-axis. So now we have to find the headroom voltage. That is we are designed for almost 150 microampere. So we are getting headroom voltage almost, we can say, around 0.6 volts. So VDS min So when it need not be exactly 150 microamps, it can be around 140 or something, yeah, 141 also is fine, because even though there is a gradual change in the VDS, but there is a slight change in the drain current, so around this value is also fine. I can say this 0.448 or 448 millivolts, 448 millivolts. So this is the minimum headroom voltage required. Now we shall determine what is the output impedance of this simple current mirror. So one of the method is a test source method, where we are giving a test source voltage at the output, where we shall give a test source voltage. If this is a simple current mirror, we shall give a test source voltage Vx, and we'll find the Ix. Let me say I'll give Vx of 1 volts and I'll obtain the Ix. So output impedance R out would be Vx divided by Ix. We are given Vx as 1 volts, so it is 1 divided by Ix. So or nothing but the reciprocal of Ix is nothing but which gives the output impedance. Now we shall do the same in the tool. So how shall we give that 1 volts? So we shall give that 1 volts by setting the AC magnitude, because we are finding the output resistance in small signal model. So we are setting this AC magnitude as 1 volt. And we have to plot the current that is flowing, that is drain current of M2. We have to do the AC analysis from 1 Hz to 1 GHz. We shall keep it logarithmic, frequency as logarithmic. And we are plotting that current. So we are not interested in this graph, DC analysis graph. So we are interested in this the current. So actually, in order to obtain the current, we need the reciprocal of that current. This is the current, we need the reciprocal. So we shall reciprocate that waveform by sending it to a calculator. In that there is a function called 1 by x, which computes the reciprocal of that function, and there is a symbol evaluate, and it will plot. So this is the reciprocal of that waveform. So the R0 value we are obtaining is 33.98. So R out is 33.98 kilo ohm. So this is nothing but the output impedance of a simple current mirror. So this is all about the current mirror, simple current mirror.